Hi all, and welcome to the Medical AI Lab talk series. I'm delighted that today we have Sameer Khanna talking to us about benchmarking Bayesian Deep Learning on diabetic retinopathy detection tasks. So looking forward to your talk, Sameer. Take it away.
Thank you. Bayesian deep learning has been applied successfully to a variety of problem spaces, such as medical diagnosis, computer vision, and autonomous driving. However, despite the demonstrated usefulness of Bayesian deep learning, there is no standardized benchmark that takes into account the importance, challenges, and complexities of safety-oriented tasks, especially those that account for the reliability of a model's predictive uncertainty estimates. The authors wanted a benchmark that is realistic, easy to understand, does not require significant domain knowledge, evaluates predictive performance, as well as evaluates a model's uncertainty performance, and can serve as a powerful litmus test for models to be deployed in safety-critical settings. They produced the Retina benchmark, a benchmark designed to be easy to use, expert-guided, and an open-source suite of diabetic retinopathy detection benchmarking tasks for Bayesian deep learning. The authors used a problem space of diagnosing diabetic retinopathy with example images shown in the figure below. The top row corresponds to images with non-sight-threatening diabetic retinopathy, while the row below shows images of sight-threatening retinopathy. Medical diagnosis problems are perfect for such benchmarks, as a misdiagnosis can lead to severe harm to patients, especially if the model confidently claims a patient does not have a disease they truly have. In general, we want a model's uncertainty to correlate with how correct a prediction is. In other words, we want a model to be certain only if the prediction is correct and uncertain if the prediction is wrong. This is important because a given data point might result in an incorrect prediction because it is different from data found in the training set due to a variety of possibilities ranging from visual artifacts, different tools used to capture data, or signs of different diseases than expected. Before we continue, it is important to understand what diabetic retinopathy is. Diabetic retinopathy is a diabetes condition that affects the eyes. Diabetes is known to cause vascular damage, in this case, causing damage to the blood vessels of the light-sensitive tissue at the back of the eye in the area known as the retina. Initially, such damage typically has no associated symptoms, but over time leads to more severe symptoms, including blurred vision, fluctuating vision, dark areas in vision, and can even lead to total blindness. There are two main stages of diabetic retinopathy. The first stage is non-proliferative diabetic retinopathy, or NPDR. This is the first stage of diabetic eye disease. Many people with diabetes have this specific stage. With NPDR, capillaries start to leak, making the retina swell. This is the most common reason why people with diabetes start to lose their vision. With NPDR, blood vessels in the retina can also start to close off. This is what is known as macular ischemia. When that happens, blood cannot reach the part of the eye known as the macula. Sometimes, tiny particles called exudates can form the retina, which can affect vision as well. If you have NPDR, your vision will typically be blurry. The second and final stage is known as proliferative diabetic retinopathy, or PDR. PDR is the most advanced stage of diabetic retinopathy. It happens when the retina starts growing new blood vessels via a process known as neovascularization. These fragile new vessels often bleed into the part of the eye known as the vitreous. If they only bleed a little, you might see a few dark floaters, but if they bleed a lot, it can block out all vision and leave the patient blind. These new blood vessels can also start to form scar tissue, which can cause problems with the macula and even lead to what is known as a detected retina. PDR is considered very serious, as it can steal both the patient's central vision as well as their peripheral vision. For the retina benchmark, the training datasets are curated from the IPAX dataset, previously known for its use in the KL Diabetic Retinopathy Detection Challenge. In order to evaluate the model performance under distribution shift, the Aptos 2019 blindness detection dataset is used to compile test and validation sets. The Aptos dataset was collected in India under a different population, using a different medical equipment, and contains distinct visual artifacts that are not seen in the IPAX dataset. Both datasets consist of 5 different classes, with 0 corresponding to no diabetic retinopathy and 4 corresponding to proliferative diabetic retinopathy. For the retina benchmark, these multi-class datasets are converted into a binary classification problem by making classes 0 and 1, which correspond to non-threatening symptoms, the negative class, and classes 2, 3, and 4, which correspond to sight-threatening diabetic retinopathy, the positive class. Class breakdowns were determined by the threshold at which a case should be referred to an ophthalmologist by international guidelines. In order to reflect real-world challenges to some degree, the benchmark consists of imbalanced classes, with roughly 19% of the data corresponding to positive classes, as can be seen in the figures below. Additionally, some labels in the benchmark are intentionally incorrect, and images also contain visual artifacts. So over time, diabetes and related illnesses like diabetic retinopathy are becoming more prevalent in the world. However, there are still relatively few cases of severe retinopathy, leading to scans of healthy eyes and mild cases being far easier to procure. It is thus highly likely in the real world that machine learning models might be trained using only a small number of scans that indicate the more severe cases. To reflect this, the retina benchmark includes a prediction task simulating the setting. Models are trained only on retina images showing signs of at most moderate diabetic retinopathy and are evaluated on retina images showing signs of severe diabetic retinopathy. For the most part, the signs for severe diabetic retinopathy are simply more intense versions for the signs of moderate diabetic retinopathy. However, severe diabetic retinopathy has additional features that can lead to complications during detection. As diabetic retinopathy progresses, additional symptoms can occur, including vitreous hemorrhaging, which is when blood leaks into parts of the eye known as the vitreous humor. For this task, the IPAX dataset is split into a subset containing all retina images labeled as no diabetic retinopathy, mild or moderate diabetic retinopathy, which correspond to classes 0, 1, and 2, and a subset of retina images labeled as severe or proliferative diabetic retinopathy, which corresponds to classes 3 and 4. These subsets are then binarized, with a subset containing at most moderate diabetic retinopathy containing both labels 0 and 1, while the subset of retina images showing signs of severe or proliferative diabetic retinopathy only contains the classes of binary as class 1. Just like there is scarcity of scans of sight-threatening diabetic retinopathy, there is a lack of scans in countries that do not have widespread screening of the disease. Thus, it is very likely that a model that can be trained in one region like the United States, where there are a lot of scans performed, and deployed in a region where scans are a rare occurrence. This can pose issues as training and test data that are not obtained from the same patient population nor collected with the same medical equipment. Examples of these images are shown on the right. These images suffer from a variety of visual artifacts, including blur, low background lighting, and effects around the edges of the retina. For this task, models are trained on images from the IPAX dataset and evaluated on retina images from the Aptos dataset. As the distribution of data shifts away from the distribution used in the training set, there is an increased likelihood of the model making incorrect predictions. To account for this, Bayesian models can utilize the uncertainty of a model to identify particularly troublesome data points where there is a high likelihood of misclassification. As we discussed earlier, in medical diagnosis, we would like to send these data points to reviewed by a doctor in order to prevent a misdiagnosis. This is what is known as selective prediction. In order to evaluate the selective prediction task, the diagnosis model is evaluated at various referral rates. Given a referral rate between 0 and 1, the top most uncertain data points are identified. If the referral rate is 10%, then we refer the top 10% most uncertain cases. The model's performance is then evaluated on the remaining data. A better performing model indicates that it's confident about correct predictions and uncertain about incorrect predictions, which is exactly what we desire for Bayesian deep learning models. It is important to note that selective prediction tolerates outer distribution examples. For example, even if unfamiliar vitreous hemorrhages appear in certain severity shift images, a model with reliable uncertainty estimates will perform better in selective prediction by assigning these images with high uncertainty, therefore referring them to an expert at a lower referral rate. In order to perform the selective prediction task, it is important to derive methods to quantify a model's total uncertainty. A model's total uncertainty is composed of two different types of uncertainty, aleatoric and epistemic uncertainty. Aleatoric uncertainty is an estimate of the uncertainty inherent in the data, such as noise in the data or target labels. Aleatoric uncertainty is also known as statistical uncertainty and is representative of unknowns that differ each time we run the same experiment. For example, a single arrow shot with a mechanical bow that exactly duplicates each launch, the same acceleration, altitude, direction, and final velocity, will not all impact the same point on the target due to random and complicated vibrations of the arrow shaft, the knowledge of which cannot be determined sufficiently to eliminate the resulting scatter of impact points. And regarding the true label given the model's parameters. If the parameters of a model are already well determined, then we will gain little information from obtaining this label. However, if we instead were uncertain about the prediction of X, then knowing the true label would increase the amount of information we have. In binary classification, the total predictive uncertainty is given by the equation on top, where F refers to the model logits and P is the binary cross-entropy likelihood function. The total predictive uncertainty is high when either the aleatoric uncertainty is high or when the epistemic uncertainty is high. In practice, the total predictive uncertainty is typically computed via Monte Carlo estimator as shown in the second equation. The parameter realizations, denoted here as theta I, are sampled from some distribution over the network parameters, and P denotes the predicted distribution of a given parameter realization. If we wish to estimate a model's predictive uncertainty in terms of both its aleatoric and epistemic uncertainty, we need a distribution over the possible predictive functions. We can obtain this by treating the parameters of a neural network as random variables and inferring a distribution over the network parameters conditioned on the training data. Neural networks with such distributions over network parameters are what are called Bayesian neural networks. There are three key differences between a standard neural network and a Bayesian neural network. First are their goals. A standard neural network focuses on optimization, trying to find an optimal point that represents a weight. A Bayesian network focuses on marginalization, which is where we treat each weight as a variable to find its distribution. Second, a standard neural network estimates its parameters using MLE, while a Bayesian network uses MAP. Third, a standard neural network uses differentiation to find optimal values using gradient descent. Unfortunately for Bayesian networks, the integrals involved are complex, and we tend to use estimation techniques such as variational inference. There are multiple methods one can use to infer the posterior distribution over neural network parameters. The simplest method is MAP. Rather than attempting to infer the distribution, MAP yields the network parameters values equal to the mode of the exact posterior distribution, as shown in the figure to the right. For a given distribution with zero mean and precision of lambda, the MAP estimate is equivalent to the L2 regularized optimization, whose equation is shown below. This provides parameters equivalent to those obtained from training a neural network with weight decay, and is thus unable to capture any epistemic uncertainty. Aleatoric uncertainty is estimated via the predicted class probabilities. A more powerful form of inference is variational inference. Variational inference is a method of approximating a complex distribution with some family parameterized distributions. Typically, this computation is extremely difficult to do by hand. For example, if we have some data X and some unobserved variable Z, we can compute the posterior distribution of Z given the data X via the following equation. If Z is a fairly simple variable, then this can be done directly. However, in most interesting applications, P of X given Z is modeled using a neural network, making the computation of the denominator extremely difficult to do. If we cannot compute this directly, we wish to find a distribution that is as close to the true distribution as possible. We thus need a metric that can quantify the closeness of a given distribution to the true distribution. One of the more popular metrics for this is the KL-Divergence, detailed in the equation above. Note that the KL-Divergence is always greater than or equal to 0 and achieves its minimum value when Q equals to P. In variational inference, our objective is to minimize the KL-Divergence between our prior P of Z given X and our estimation function of choice Q from a family of functions big Q. Unfortunately, computing the KL-Divergence directly is difficult. As shown in the equation above, computing this metric involves computing P of X, which is typically intractable for the problem spaces we wish to use Bayesian neural networks. Luckily, since we only need to minimize the KL-Divergence, we can optimize another objective, in this case, the elbow function, as shown in the equation below. The elbow is equivalent to the log of P of X minus the KL-Divergence. Thus, maximizing the elbow function allows us to minimize the KL-Divergence without needing to calculate P. There are a couple of different variational inference models discussed as used in the Retina benchmark paper, which we'll go into detail about now. As before, Theta represents our model parameters. In this case, we can assume that we have n such parameters. As you may recall from the previous slides, in order to compute our estimates, we'll have multiple integrals or summations, one for each of the theta i's. The mean field approximation is a simplifying assumption for a family distribution, which partitions the variables into independent parts, simplifying the computation as a result. The resulting variational objective allows one to use stochastic variation inference and thus can be trained via traditional gradient update methods. This is what is known as mean field variational inference. For Gaussian mean field variation inference, the network parameters are reparameterized as shown here. For radial Gaussian mean field variational inference, it has the same variational objective, prior, and variational distribution as standard Gaussian mean field variational inference, but uses an alternative gradient estimator to obtain an improved signal to noise ratio in the gradient estimates. The network parameters are reparameterized as shown here. For function-space variational inference, we find that by using a locally accurate linear approximation of network parameters, as shown here by this equation on top, we are then able to perform stochastic variational inference and thus use a traditional gradient update function. For the retina benchmark model, a Gaussian mean field distribution is defined over the final layer of the neural network, which is parameterized as shown below and as seen in the previous slide. It has also been shown that training a network with dropout and L2 regularization, solving the optimization problem as shown above, approximately corresponds to variational inference in a Bayesian neural network. This is simpler than alternative methods, as in order for us to sample from the posterior distribution, we simply need to apply dropout to the network parameters. And finally, in rank 1 parameterization, we parameterize the weight matrix using W, R, and S, which combine to form W prime as shown here. The weight matrix W is trained using the loss function shown here. As can be seen, W is treated as deterministic and updated and trained via MLE, while the vectors R and S are trained using a variational objective function. The name rank 1 parameterization comes to the fact that both vectors R and S are rank 1. As this is a benchmark dataset paper, there are no new model architectures, training techniques proposed, or uncertainty estimation methods proposed. A variety of methods, which we just went over, were used alongside their ensemble analogies. Each model baseline is implemented in its own self-contained experiment pipeline in order to minimize external dependencies and make it easier for practitioners to experiment with a given model. The authors use a resonant architecture for all experiments, with a sigmoid applied to the final linear layer of the networks in order to obtain class probabilities. At training time, no shifted domain data is provided to the models. This is meant to simulate scenarios where we do not know what data or distributional shift the model might incur during deployment and thus cannot make assumptions about it at training time. All images are pre-processed via the procedure used by the winner of the KL-Diabetic Retinopathy Detection Challenge. Images are rescaled such that retinas have a radius of 300 pixels, are smoothed using Gaussian blur, and are clipped to 90% of the original size to remove boundary effects. Here, we can see examples of both the original images on the left and the corresponding processed images on the right. For the severity shift task, models are trained on iPad images that show signs of at most moderate diabetic retinopathy and are valued on scans showing severe retinopathy. The authors found that models generalize well under this shift, performing no worse on in-domain examples than shifted examples. In fact, as we can see in figures A and B, the models had a higher AUC under the distribution shift. Models under this task also provide good uncertainty estimates with predicted performance increasing monotonically as the referral rate increases. This means that at deployment time, we can choose a referral rate that leads to a desired model performance or determine a model performance based on a set referral rate in order to balance accuracy with respecting the time of experts. As the referral curve is monotonically increasing, the optimal referral rate would be the maximum acceptable referral rate. It is important to note that these results also highlight the importance of taking into account epistemic uncertainty. For example, Monte Carlo dropout, an uncertainty estimation technique that incorporates both epistemic and aleatoric uncertainty, achieves predictive accuracy at a referral rate of approximately 50%. This is the referral rate that is nearly 20% lower than when MAP, which only represents aleatoric uncertainty, achieves this. However, not all variational inference models follow this trend, with some models performing worse than MAP. The authors note that these results underscore the importance of their benchmark as it facilitates continued research in Bayesian deep learning. Next, they investigate how a model's predictive uncertainty estimates vary with respect to the ground truth clinical label. Examples are first binned by the ground truth label. Then for each method and label combination, the distribution of predictive uncertainty estimates for correctly and incorrectly predicted examples are plotted. Here, blue corresponds to correctly predicted examples and red corresponds to incorrectly predicted examples. An ideal model that produces reliable uncertainty will have most of the blue distribution mass around a low uncertainty, are on the left side of each plot, while most of the red distribution mass should be around a high uncertainty or on the right side of the plot at higher x values. All histograms here are normalized and are displayed with the same range on the x and y axis. Some bars of the histograms are cut off because the plots are zoomed in along the y-axis to improve legibility. These histograms here, plots for the severity shift tasks, indicate that the same thing as the AOC plots on the previous slide do. All Bayesian neural networks perform decently in terms of how well the uncertainty values indicate correct versus incorrect predictions, with incorrect predictions mostly on the right-hand side of the plots and correct predictions on the left side. For the country shift task, models are trained on the IPAX dataset and are evaluated under distributional shift on the Indian Aptos dataset. The black dot in figures A and B refers to the minimal sensitivity specificity threshold for the deployment of an automated diabetic retinopathy diagnosis system as set by the British National Health Service. On the in-domain set, only Monte Carlo Dropout and its ensemble meets the standard, whereas on the shifted domain, all models surpass this threshold. This would typically lead a practitioner to think that their model generalizes well under this distribution shift. However, the ROC curves do not provide information about model uncertainty and uncertainty estimates. Indeed, if we look at figures C and D, they paint a vastly different picture. As we can see, on the country shift task, most methods fail, with predictive performance on the shift task actually declining as we reach referral rate, indicating that the model uncertainty estimates are no better than simply randomly selecting instances to refer. We see that numerous models reach well below a 90% AOC score, then plummet down to a score below 60% as the referral rate increases. Using uncertainty to refer patients actively hurts model performance on the shifted dataset. If a practitioner were to only focus on the standard performance metrics, they might wrongly conclude that their models will perform well as a part of an automated diagnosis pipeline, which clearly is not the case here. The histogram plots for this country shift look vastly different than analogous plots for the severity shift that we saw earlier. In some cases, incorrect predictions are spread across all uncertainty levels. In others, both correct and incorrect predictions follow similar distributions. And in others, the incorrect predictions have low model uncertainty, while the correct predictions have high model uncertainty. It is clear that using model uncertainty to determine which examples to refer and which examples to use the automated diagnosis for does not work for this task. This table here shows corresponding quantitative results for the country shift task. The main takeaway for this table is that rankings of models change drastically based on the evaluated task. The authors noted that these results underscore the importance of generic evaluation frameworks like Retina to enable rapid benchmarking of many tasks. In previous work regarding Bayesian deep learning, there's no real standardization regarding whether a model has access to shifted data for hyperparameter tuning, and this is often changed on a study-by-study basis. The authors contend that having access to this data has a significant impact on metrics commonly used to assess the robustness of models. In order to consider the performance of our baseline models under the assumption of having access to some shifted data, they developed the accuracy referral curves shown here. As the in-domain validation set is significantly larger than the distributionally shifted data set for either task, the authors upsample the shifted data set to prevent the in-domain examples overwhelming these shifted examples. This is done by duplicating the shifted validation dataset many times as possible without exceeding the size of the in-domain validation dataset, and then randomly sampling examples from the shifted validation dataset without replacement until the sample shifted dataset contains the same number of examples as the in-domain validation dataset. The joint validation dataset is composed of the union of the upsampled shifted validation set and the in-domain validation set. For this experiment, they focused on the country shift task. The left side of the figure corresponds to model performance using only the in-domain validation AOC for hyperparameter tuning, while the right side uses a combination validation dataset. Even without having the model explicitly trained on the shifted data, using this data for hyperparameter tuning leads to significant boosts in prediction accuracy, as well as uncertainty estimate quality, as can be seen by the steeper slopes and curves in the right figure compared to the left for referral rates up to 50%. In conclusion, if you want to deploy modern machine learning models in safety-critical real-world settings, we need to be able to trust the reliability of a model's predictions, especially in safety-critical real-world settings. To the end of encouraging the development of Bayesian deep learning methods that are capable of generating reliable uncertainty estimates about their predictions, the authors proposed the Retina benchmark, which is a set of safety-critical real-world clinical prediction tasks. They show that this benchmark highlights various shortcomings of existing uncertainty qualification methods and demonstrate that selective prediction can help identify whichever methods might fail when deployed as part of an automated diagnosis pipeline, while standard metrics like AOC fail to do so. The Retina benchmark was designed with the hope that it makes it easier to assess Bayesian deep learning methods on safety-critical real-world prediction tasks. Thank you.
Thanks a lot. Thanks, Sameer.